Yeah, I think it's on.
So I did not record the introduction, but I will record it from this point onwards. F5. Let's see if it works. Now, I volunteered for this course. It was my idea. It's not typically a part of the course, but recently we have lost two very good teachers who were teaching FEM specifically. And they used to have examples of how to make 2D elements, and you would go through this long course of coding it yourself. It was super hard, but it was super in depth. And technically, if you did good in that one, if you passed with a 12, you are guaranteed to be able to code your own FEM engine. The ability was there if you had a good grade. Perhaps the focus has shifted from making our own FEM software because there's so much of it on the market right now. But I still want you to have a very basic understanding of what is the essence, the core. And at the end of this workshop or lecture, the name has been changed a few times. At the end of it, I hope that you have an idea what is the difference of applying a force on a structure and what is the difference between applying a displacement. That's technically the main message. If you apply a deformation, the mesh, it can be any kind of shape or geometry or structure, it kind of finds the reaction force that matches the applied displacement with the, and it shows you how much force it's producing the displacement. And there's always a solution for that, and because you know the displacement, you're just holding it and the whole structure just keeps wiggling around and looking for an equilibrium point. If you apply a force, you can imagine this box here is a nonlinear system. There's some stiffness, and then if I push it too hard, it moves. And the deformation stays. So it's plastic deformation right there. You can push your laptop on the table, for example, and you will notice that you can touch it, there's a reaction force, and then if you increase it a little more, it moves. Similarly, in simulations, if you apply a force and the physical system cannot generate the reaction force, what happens is the engine cannot find a solution. So you apply a force, it starts moving, and the engine just goes infinity. So when you're looking for a maximum force in a plastic system, and soils are always plastic, there's a very, very small amount of elasticity in it. When you work with a plastic system, your task is to find if the thing can survive an applied force. But technically, the simulation is not stable at that extreme if you apply a force. So one approach is to say, we apply this force, and at the point where it fails to solve it, that's the maximum. Another approach is to keep applying more and more deformation, and then you record this curve and you say the curve moves. And I want you to be aware of both loading options very consciously, kind of understand the difference, because it also happens in the real world. If you are testing something by applying a force and say a stick in the mud, simple example, you apply a force, it starts moving, and then it's no longer static, it's no longer a spring that floated, it starts having a velocity, which means water starts moving. You have a viscosity all of a sudden. And if the acceleration is fast, you even have inertia forces. So if you apply a force on a real structure, you're not just pushing it, you're actually mobilizing all different parts of the equation of motion. You're applying a static load, and you're getting a viscous effect, and you're getting an inertia effect. But if you apply a deformation, if you control the deformation instead of the force, you're kind of controlling the velocity. You can apply it very slowly until the load is there, and maybe there's a drop in resistance, no problem, the formation continues. Maybe there's an increase then. But if there's a gap and you apply a force, like and it goes down. We deal with this a lot in the lab. And if you don't have the background, if you don't understand exactly what the algorithm is doing, the piston controllers and so forth, it can lead to problems. And you end up measuring this kind of, and you're saying, oh, that's a soil. No, that's not a soil property. That's a property of your PID algorithm that's controlling the hydraulic piston. So to differentiate between properties of the equipment and the properties of the specimen, this will be helpful. And also that will carry on in your later decisions because most of you will be responsible for real project in the real world. And I want you to have some doubt on what numerical results really mean, to understand the limitations as well as how to improve them at that point. So here is an example of Plaxis. And when I was a master's student, we were doing this lab test in the wave lab, where I have to check time. Yeah, in the wave lab where we did a few waves past the pile, and then we collected those loads, and then we were supposed to take the peak. But I was disobedient. I found the entire loading curve of the whole frequency in 1,000 points, kind of high detail. It was a stream function, 7th derivative. And oh, it's shaking, interesting. The bus, you can feel it, the air construction side there. Anyway, and then I wanted to make a simulation with all the loading points, and the supervisor came in and he said, it is not necessary to make the whole loading sequence, you only need the peak, it's a mistake, and it's impossible to do a dynamic simulation in Plaxis also. Like, as soon as I heard impossible, I spent the next 54 hours without sleep doing it, and I did it. And this is the result, these two figures here, which are animated. You can see 3 waves hitting it. And then in the defense of the project, the same supervisor, I was saying, it's possible. And he's like, yeah, but it's nonsense. Because soil properties are not captured by the models precisely. The cyclic loads are not captured properly. You can get the peak force, but the stiffness is questionable. And when it comes to cyclic loads, it's an unsolved problem. And I was like, what's missing? Like, nobody knows. And I did a PhD about that. And I spent nights and evenings working on that question. During the days, there was a topic that's safe. And in the evenings, I could do something that is ambitious. And after 3 years, I convinced my new supervisor to allow me to publish the ambitious. And it's quite leading nowhere so far. But still proud of it. Those 3D simulations take a long time to compute. But if you have springs, and this is something I did from my PhD, if you have springs, you can implement new models and you can capture kind of like layers of soil, capture them from 2D into 1D. This is just one spring attached on the side of this pile. And the pile has stiffness made of metal. And then I was trying to capture these disturbed soil properties as you go through irregular loading cycles. So there's impact loads, there's cycles of small amplitude, big amplitude. I started modeling them on a triaxial test on a specimen, and I then tested it on a small foundation. I observed these behaviors, and they were really complicated to describe in a kind of small elements, mesh 3D. So I did it with small springs instead. And this method is actually used a lot in the industry, especially in these simulations where you have probabilistic analysis. You need a large statistical average. You need to change 1, 2, 3, 4, 5 different parameters 1,000 times. So 1,000 times 1,000 times 1,000 times 1,000 times matrix of parameters. You cannot do that with a simulation that takes 2 days or 2 weeks to deliver. You can only do that with a simulation that it's like fast, because you need a lot of data points. So you sacrifice some precision from that 3D model, you calibrate it to capture most of it to some degree, and then you can get your answer, at least an estimate, realistically. And that can be done with the most basic finite element. So has any of you tried to code FEM before? Not very enthusiastic. Okay, do you know what the degree of freedom is? Nice. So 2 degrees of freedom, one on one and one on the other. You can have rotation if you wanna, you can have shear force on both, you can have an axial load, which is the simplest to illustrate. And that's it. You pull this one, that one feels some reaction through stiffness, E or K, whatever stiffness there is. And that's an elastic element. And if you want to do it in 3D, then every one corner has some degrees of freedom, but this remains the same thing. Technically, if you lock all of them in space, just anchor them in space, and then you release 1 degree of freedom. You build that stiffness matrix by moving this by 1 unit, and then assigning force distribution on all the other corners, technically. So when you pull it by 1, it creates some reaction force that you must know somehow. You can test it experimentally. Or you can use some advanced field equations to distribute it through this field of this imaginary displacements, imaginary work functions. So you move it and then get some reaction force from displacement of 1, and then measure the rest of them. And that's how you can build elements. You can do it by physical measurements, you can do it in theoretical, both work. And then you have some number of parameters controlling the stiffness, and this is all elasticity so far. And elasticity is amazing in the sense that if you have millions of elements connected together and you move one of them, you do this equation here, and like magic, you move 1 degree of freedom, it gives you some initial force distribution within the element, and then these forces are put on the elastic, and you get the solution of final displacements of the whole million nodes. So this is a magic equation. There's a lot of math in it, but you can apply it in this kind of redundant, simple way. You can make anything with it. It's quite amazing. The only problem is it has to be linear relationship between the elements. It's elasticity, and it's kind of hard to imagine how to modify this mesh, because the only thing you can do with elastic ones is you restrict some degree of freedom. You say you cannot move in this direction, and also if you anchor it, you can pull it and say, I know the position of this. So technically you either know the position of a node, or it's floating freely in the air, and you can apply a force on it. So something has to be anchored, otherwise if it's just floating, you apply a force, it just floats off in infinity. So you anchor it somewhere, and you can change the position of the anchor if you want, using the first equation there. And then afterwards you apply a force on it to move it, and then you find the displacement on the floating one, the free one. And that's all you can do with elasticity. Elasticity cannot do anything else. After it moved, the force was applied, it moved, the distance between the points changed, and you can calculate what the stress is, or the pressure, or whatever it is, the element inside. As long as you know the stiffness, you just find the properties. And then it doesn't change once you add plasticity. It still runs on top of this elastic background, elastic core. But what you do with plasticity is you generate artificially some internal forces. I'll call them internal. They also call them plastic increments. But plastic increments is just a value that says, I'm going to apply a force that produces this amount of plastic deformation. That was something that was really hard for me to get when I was studying this topic. It was so heavy in math. But technically, all elasto-plasticity does this thing, where you have an elastic mesh, in this case a spring, and it's only forces that can really deform it. If something is anchored, it's static, it's done. But because only forces can deform it, you need to convert these plastic increments into some kind of force on the nodes that will shape it into the plastic deformation that you want. So I will take a small break here to let you imagine a case where, like, try to imagine a simulation where you have a spring of a certain length, and the spring is modeling maybe this box on the table, and you can apply some amount of force without moving it, but then it moves. And so you have to find the force which moves the spring this far, and then hide that force inside there. Like, you are deformed this much, the force is constant. Like, no, there's no outside force, but inside the elastic element, it's actually held in place. It's a little awkward. It's a hard thing to imagine. But once you have it, it really helps. And then it really explains what all of these elastic plastic models do, because I know that you later in the course have a lot of very advanced plasticity theories and models. But that's what they do. They control the length of the spring by preserving it in plastic deformation increments. It's easier for the brain to imagine that, like, if we have 10 centimeters of plastic deformation, then I know that the box is 10 centimeters deformed. But the way the code interprets it, it converts this 10 centimeters into a force which will change the length by 10 centimeters. So it's a little back and forth. And then comes the stiffness matrix. Is everyone familiar with the stiffness matrices? Yeah. Good. Oh man. And Bidoff, the boundary conditions. Do you know what that means? What it implies? Okay, so Bidoff is technically you're removing a column or a line from a stiffness matrix. Like Friedhoff is parts of the matrix that are being computed. Bidoff, the boundary effects, are the parts, columns, and rows of the matrix which are not being computed. So by changing the Fdoff and Bidoff, you're technically selecting certain pieces of the matrix. If you have one element, it's just one. If you have multiple of them, they connect in the corners. Like these nodes that are shared, they end up summing up the stiffness in a specific node. And then as you have a Bidoff right here, for example, on the first one, 1 degree of freedom in this case, you just eliminate a column. And if the output is Bidoff as well, then you eliminate a row. I like to imagine matrices as a kind of a, yeah, that's how you sum it up. I like to imagine matrices as this kind of a, the vector of displacements is thrown on top and just drops on it. And then multiply everything and spits out. So, and then spits out another column. And then if you want to multiply next matrix, you just lift it, flip it, and it drops another column out. And that way it's very easy because rows get cancelled, columns get cancelled. And so then the math becomes very visual. Some people say there's no such thing as a visual thinking, but I really see things in 3D. And I do math in 3D data structures in my head. I'm really bad at the actual algebra, where you have to add two numbers together, because 5 times 2 for me is 2 squares of 2 and a 1/2 next to each other, and then it's like 4 squares and 2 squares, and that means 8 plus 2 is 10. I like to think graphically about matrices, and that's why this method works for me so well. So this illustrates the point. And I want you to notice this, again, is magic. It's just raw magic. You apply a deformation on a prescribed degree of freedom. It's basically boundary with the applied displacement, Bidoff. And then you plus with the Bidoffs, well, technically these are zero displacements applied. This is some kind of displacement applied on an anchoring point. Multiply on the K, you have the initial distribution of forces next to this element, because these are anchored points. You cannot apply a force on it, you can only apply the force on the neighboring elements. So you apply the forces in the neighboring elements with this part of the equation. You can insert this in here. And then once you have all the forces from the outside, you can also add forces of your own on this one, external forces. It can be like a load on a specific node along the structure of a shaft. You add them here, there's a plus sign. And then, no matter how big the matrix is, million by million, I don't know how long it will compute, but you inverse that, and this is a MATLAB command, automatically it finds the optimal algorithm. There are many different algorithms to inverse a matrix. So you inverse that, and you get the distribution of displacements from the displacement you applied, plus the forces you applied. This is magic, that's elastic. Plasticity adds a second plus here, where you have these invisible plastic increments being converted into external forces. And yeah, so you know how to assemble the stiffness matrix. I checked by asking. Yeah. And this again was graphical thing, that this means all the columns are selected, and that means only Bidoff lines are selected. Everything else is filtered out. So once you have the final displacement, you multiply it on the matrix and it gives you all the reaction forces. And then you can play with the plus and minus sign to check if it has to be plus or minus. Yeah, it chooses me every time. So yeah, so now at this point you can find the reaction forces. So after you run all of this simulation, you get the F-DOF movements. Once you have those, flip it back on the matrix, multiply, and you have the reaction forces on the degrees of freedom which were not part of F-DOF in this part, because we have only U F-DOF and there's no F. There's no FB-DOF in here anyway, so that's the last piece. That's the full circle. You find the reaction force and the applied force. Yeah. Any questions? Okay, I made this presentation in such a way that the math is super simplified. And my hope is that if you ever end up in a situation where you have to build anything that's interacting kind of elastic range and plastic range, like you want to simulate a box on a table, or maybe you want to simulate a structure which has some kind of friction driven stabilizer. Like in earthquakes, you have these masses that move, and the building starts moving, the mass cancels it out, and then a bit of inertia there slows it down from moving. So you can have all kind of nonlinear systems designed using super simple math. It's like plus 2, u plus u times k equals F1. And then u plus F2, your external forces, and F3, your plastic compensating forces. Inverse k, you have the distribution of displacements from the entire system, no matter how big. And that reaction forces get the F-DOF. Full circle. And in all plasticity simulations, this is the circle that keeps going. Sum of the displacements, forces, reaction forces. Next step, something change. Maybe you change the load. And in plasticity, there's this iterations of adjusting the third F. So apply the formations, apply the forces, and check if the reaction force matches the prediction of model. Doesn't match, adjust the plastic forces. Check if it matches. Doesn't match, adjust the plastic forces. Check if it matches. Does it 1,000 times. The bigger the mesh, the longer it takes, because every node shakes in its own way. It's super time consuming. And that brings us to the second part. Yeah, this is what I just said. Elasticity, plasticity. How do you get this system to behave like this? I think you already know the answer. And this is, by the way, a real test from a real triaxial simulation. And this is the thing I discovered, that if you apply the formation of this size and keep doing it, the hysteresis loops have a constant shape. You increase the confining pressure, keep the same amplitude, the strength increases, the peak, but it doesn't really change the general shape. If you normalize it, it actually overlaps with the previous. And then you stop here, increase the confining pressure more, strength changes, and then change the amplitude too. And then now, after 2 cycles, the triangle is here, and then if I reduce the confining pressure, stopping around here, you have another triangle. So it's not a line. The stiffness path is not a line. In elasticity, the stiffness path is a simple line. In reality, many systems don't have a line. And the hyperplasticity is a type of nonlinearity where you always cross the 0 point. So some models can be okay with that. Maybe you don't want to calculate dissipated energy. You just want to see when the whole thing loses its strength. And if that's the case, you insert some kind of log normal or exponential curve, and it can do the thing. This would be like a wall. Something bounces into it. You have that in, for example, computer games. Computer games still use this theory, like collision detection boxes. And maybe you want something that's very rigid, maybe you don't. This can cause instability, because if you guess a displacement up here, all of a sudden the reaction force is infinite. And then how do you compensate for an infinite reaction force error? you compensate by adding an infinite displacement backwards, and it explodes. Have you ever seen on YouTube channels those cases where some kind of shooting game happens and some player gets killed, and then their doll, this doll, falls down and starts shaking, and like one hand gets stuck somewhere and into space and shoots out? That's the reason. So yeah, a lot of interesting glitches can happen. And in elasto-plasticity, normally, it's pretty hard to have smooth curves. You usually have this kind of shifting of the stiffness path back and forward more long. Then the casual method of dealing with it is to add more yield surfaces. So some different plastic increment that starts from here and from there is just flat. And then if you unload, you go through the envelopes, you will get that in a minute's lectures. And that's elasto-plasticity, that's hypoplasticity. But there's a very small difference between them. Technically, both of these run on top of the elastic mesh. It's still the same thing happening. You have a point, and you look for the displacement, the plastic displacement, or a relaxing stress, which would provide that force at that position, or that deformation at that position. Balancing reaction force with the applied force. Yeah, and this again is the point. Yeah, this equation is so magical. It's amazing. Have you seen this before? This increments of error reduction. That's how all the plasticity formulas are solved. Technically, there are different methods of choosing how big the next step will be, because you have some plastic correction happening here. Like, this is the elastic prediction, and this is the physical or plastic curve that you want the element to actually follow. So if your elastic spring will say at this force, this length, but you want that spring to have this length at this force. So what happens is you add a plastic increment. Let's call it plastic strain increment. And what plastic strain does, it adds this kind of internal imaginary force that makes it this much longer. And then for humans, it's convenient to say, okay, the next, I have this distance from the actual curve that I want to be on at this point. So what do? I add this error, I convert it into an increment, and I have this much more plastic deformation. Plastic. And for the humans, it's very good. Plastic deformation this much. And then the algorithm looks at it, this much plastic deformation means I need to add this much force compensating, and then I can pull the string like here, and so forth. It keeps going. And as closer you get, the harder it gets. Less and less correction happens with every step. At some point, it starts converging slower and slower and slower. And there's hundreds of different algorithms to do it. There's PID controllers, there's Runge Kutta, and all kind of derivatives of different degrees, adapting slides. And then you have a million elements all trying to wiggle around into positions. You cannot put it in your head. You will have to run simulations of that. But be aware that this is what all iterative convergence solutions do. They make a guess using elastic. That has to be here. Like, I want to be on this curve, so I'm this far from this curve at this displacement. Okay, let's add this here. Okay, I'm this far from the curve I want to be on. Let's add this here. That's a million times. And you always set a threshold how much error you tolerate. So if you tolerate 50% precision, you're gonna be like, yeah, this is fine. It's close enough. If you put 0.001%, like, I want the absolute truth. First of all, no models deliver truth. It's not a physical reality. It's an assumption of generalizing. But I want absolute truth. 0% tolerance. Like, you're gonna go until infinity, wiggling inside this invisible tiny piece. You're gonna run out of floating space digits. Like, yeah. So you gotta make compromises. You want to go fast and have an assumption of approximately what's going to happen, and then apply a safety factor of 2 on it. Like, who cares? Safe enough. Or do you want to get into this perfectionist trap where you want the most advanced models with the longest convergence times to give you an assumption. Your choice. And yeah, I tried to expand this further. So these internal ones from the previous slide, F applied on degrees of freedom, and forces from boundary condition displacements. Inverse, poof, 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 and that's the delta here. That's the coefficient you choose. How much delta will you tolerate? Too much error, globally, locally? Do you want the entire system to have a certain percent of error total, or do you want the error to be no elements with more than 1% error? Or you choose, your choice, whatever you want. There's many options there. All the software has it. And now comes the last part. I hope my camera is still running. Yeah, it's showing some kind of time. Oh yeah. Teachers trying to be cool. Right? Nothing is more cringy than that. I'm still waiting for to get older, 10, 20 years, get a little older, maybe the nose will grow, the ears will grow, and then maybe your hump nut forward, and then I can be super cool, making some kind of game references from 2005 and it's 2040 by that time. Quake references. Yeah, I have prepared you an exercise where you can choose many different curves. You can use the log normal. If the curve is flat like this, you will wait a long time for it to converge, because it will get into a zone where the distance from the elastic plus plastic corrector, the distance from the line is very small, and the curve keeps going. So you're just gonna spend half the day incrementing across it. In that situation, you may want to use something that adds up the previous guesses, kind of accumulates the displacement. So here, maybe if you made 100 guesses and the error has become very small, maybe you want to artificially scale this up. So instead of compensating with this, you multiply it by 5, and you have done 5 times bigger step, and the curve is really flat, you can kind of make bigger steps, right? If the curve is exponential, well, then you're gonna get stuck in a place where you jump and fall back, error, fall back, error, never hitting the sweet spot. So at that point, maybe you want an algorithm which artificially reduces the step. If the curve is almost vertical, well, maybe you can kind of modify this error corrector to apply 1% of the actual distance, and then very carefully crawl along the wall. It's just one step can explode completely. You have the examples there of that. And in that MATLAB code, you have a super simple system, and it has the option to increase the number of springs. There's technically one spring is plastic, elasto-plastic, and one is pure elastic. And this is the same spring system, it's just this one is fully elastic, this one has this spring modified to be elasto-plastic. And then you can choose any curve you want to apply on this one. I leave this one elastic because I want you to see that the elements interact with each other. So if you apply a force, the length of this one and that one will be the same. If you apply a displacement, like this case, this is the green one's initial position. You apply a displacement, these two are equal because they are elastic, they have the same load on them. But here, the displacement is fixed, so the plastic spring is releasing something. It's not as stiff. And you can even do things like waves propagating through nonlinear materials. Like it's possible to generate triangular waves to make waves. With this type of simulations, you can make waves which collide with each other, and the space stretches, and it's weird stuff you can start doing, but I will not go into that. Just be aware that the potential of this has not been fully explored. There's a lot of focus on how to make the same algorithms run 2% faster, but very little research is actually being done on how to compute it differently. And there is a way to make nonlinear waves travel through nonlinear elasto-plastic medium. And there also probably is a way to find how to compute these things in pure parallel. Right now, as it is, the theory relies on math which requires repeating the matrix inversion every time, super computation costly. And it also relies on finding the stresses inside each element in series, one after another, and then converting the stresses into a plastic strain increment and a plastic strain increment back into some kind of force. There is a method where you just take the force and forget the plastic increments completely. And then all of a sudden you don't need to go through local element by element micromatrix inversions. It makes it possible to put everything into one continuous parallel vector math format, where you just flip a vector in, flip a vector in, flip a vector in, two vectors together in matrix. And that would make it possible to run simulations on supercomputers. We still don't have a finite element elasto-plastic concept which runs on supercomputers. But there is a way. And if you choose to develop that, well, then good luck. You're going to run into some heavy math. But if you know someone who's I don't know, like one of those people who cannot tie their shoes, but they're super good with space-time continuum parallelizing, that might be interesting to them. Yeah, so let's see if this animation runs. I will just quickly show you what you are about to see in your project. Yeah, so guess what that is? Different displacements applied, convergence failure. Can you guess why it fails? Probably exponential curve. Logarithmic curve, super slow. Logarithmic curve, yeah. Zero resistance, yeah. Still error is huge, yeah. Yeah, this is very much like what you're gonna do when you start actually simulating. Yeah, but the error is dropping, right? Yeah, very good. Yeah, let's try something like that again. Error tolerated completely. Oh no, now it's actually zero probably, yeah. Okay, and so forth. So in the code, I made the code in such a way that it runs out of the box and parts of it are commented out. You just uncomment and it continues to the second stage. And then you can have a few options of different functions for plasticity to choose. And it comes with a file that says which formula to insert where. So if nothing changed when we copy pasted the course, then you will be able to just step by step follow it through. And the task, the challenge is to describe what you are seeing. Like this element converges super slowly in this case. And the reason is because, well, you try to explain it in your own words. I want you to improvise with your own way of describing things. Because I personally have a really hard time following text. For me, it's very important to see the picture, that the entire thing in 3D in my head. When I sleep, I dream. When I don't sleep, I daydream. It's all pictures, all things moving into each other, numbers flowing into boxes, vertical, horizontal. That matters to me. And when I see this, it makes me understand things like, okay, if I have a pile in a sandbox and I apply a force, maybe it's gonna, the elastic is the pile, this is the soil. So it's gonna interact with that, and the top layers are gonna give out, and then it's gonna take forever. Maybe I can adjust the settings of compensating for error differently, and so forth. I mean, if there's a distance between two objects, but you have collision detection, one object starts bending and then touches the other one. Infinite stiffness at that point, like, or at least the stiffness of the next object, but your guess is not gonna start with an exact match, it's gonna start with that object behind that one. And it's like, oh, there's a problem, you hit a collision box, and there's a distance like that, okay, how do I compensate it? Well, first of all, maybe I reduce this one, but then it doesn't have enough strength, and I have to pull them together somehow. It becomes very interesting. I actually met a few guys who were doing this kind of things, and it's quite interesting. Yeah, so that is the lecture that I volunteered to do because I think there is a gap in curriculum due to very great teachers leaving for another university in the recent years. I hope we find ways to fill that gap through, at least to some degree, with this lecture. Thank you.